There we go. Welcome, everybody. Lights adjusted. We are in lecture 7. How did everybody enjoy their 3-day weekend? Well, okay. Normally, or at least for the past, 10 years since I've been at Marshall, we would be in it for nonstop between now and Thanksgiving, but the university is installed an October break. So we will have another 3-day weekend coming up, but that's not for a little while. That's like a month from now. So for now, we're in structural analysis land for a good little bit. Okay, so we finished reactions last time, the last homework. Did that go well? I hope so. Our homework grades are caught up. We're up to date on everything on Blackboard. You're getting your first truss assignment today. We are starting a new topic today. We're going to start plain truss analysis. Okay. I imagine everybody in here has done truss analysis at some point. If you did it in statics, it's probably the place that you did it. You might have seen it a little bit in 216, but for the most part, everybody probably did it in engineering 213. We're going to do it again in here, but we're going to delve a lot more deeply into the world of trusses. When you do it in statics, you only do it for a day or two. We're not going to do it very long we're only going to have 4 lectures on it, but we're also going to revisit it when we look at deflections and influence lines and things like that. So we'll be seeing just because this is our pure topic on truss analysis, we'll be dealing with trusses a good bit throughout the semester. Okay, did everybody get the code? Everybody got the code? All right, so let's delve in to trusses. Okay, so a lot of times when we begin a new topic in here, and I guess I use the term new in quotation marks because, again, you've seen trusses before, but whenever we begin a topic like this, I want to start off with our assumptions. And I do that mainly to sort of, I guess, unconsciously reinforce the idea that what we are doing is not analyzing structures, but mathematical models that represent them. So what that means is we need to understand what are we assuming as the underlying behavior in these assumptions, so that when we start performing the analyses, that it makes sense, that it comports with what we're assuming the behavior is. Okay, but I want to take a step back and go, well, let's make sure we're all clear on what we mean by trusses. Trusses are arrangements of straight members that are intended to form a structure. And primarily trusses are going to form triangular patterns. Okay, so the 2 most common applications for trusses are bridges. You see trusses used for bridges. You also see trusses used in roof systems. Okay, so I've got an image of each of those here. The thing about a truss, if we're talking about structural behavior, trusses are very stiff. Okay, now I use that term very specifically. You might think of the term strong and maybe the term stiff as meaning the same thing. They don't. Okay? And strength and stiffness have very specific meanings in the land of structural engineering. Strength refers to how much force a given system can withstand before the system fails, before it falls down and kills somebody. That's what strength is. Stiffness is the relationship between applied forces and resulting displacements. Now, are strength and stiffness related? Yeah, for the most part they are, but they're not the same thing. Trusses are very stiff. Okay, whenever we're designing structures, we have many limits that we must achieve with a given structural design, and a lot of times we have to deal with both strength limits and limits related to stiffness. So, as an example, if you're designing beams in a building, okay, let's take a building like this. Okay, so I've mentioned this before, but there are floor beams carrying the weight of the floor above us, that are carrying the weight of the floor above us, and must support all that load. So obviously we need to size those beams in order to be strong enough to be able to withstand the forces. But we also have to design the beams to be stiff enough to achieve certain deflection limits. So a common deflection limit that we will design for in structural engineering is L/360 in building applications. It's a little bit more stringent in bridges. But in buildings, L over 360. So what we'll do is we'll take the length of the beam, divide it by 360, and we'll get a number. Let's say it's like, I don't know, 1¼ inches, whatever that is. The beam cannot deflect more than 1¼ inches under its, live load application. Now, there are reasons for that limit. And in fact, L over 360 comes from installing roof beams for plastered ceilings. How many of you have ever been in a building that has like a plastered ceiling, like an old type building? So what happens is if the beam deflects too much, if it deflects over L over 360, the plaster will start to crack. That doesn't mean that the beam will fall down and people will die, but it also doesn't mean that if you are installing a roof beam that you won't plaster crack. So there are two different questions, right? One, is it strong enough? And two, is it stiff enough? And sometimes when you're designing a structure, the stiffness matters more than the strength. Or the stiffness is going to be what governs your design. When you all take either reinforced concrete design or a steel design class or something like that, we get all into that. That becomes a big star of the show. But suffice it to say that trusses are very stiff systems, and they resist deflection very, very well. Now there is a that's one upside. Let me mention another upside. Trusses are light. Okay, if you compare, so let's take this bridge right over here on the right. If I were to replace this bridge with a comparable, let's say, beam and slab system, there is a very good chance that system would be heavier. Okay, trusses are light and they're stiff. One of the downsides of a truss, though, is that it's expensive. Okay, trusses. So let's take, for example, this truss over here on the right. Trusses require a lot of cutting, a lot of drilling, a lot of welding, a lot of shipping, a lot of different pieces have to be put together, a lot of labor that goes into it. So if you're going to use a truss, there better be a good reason for it. Now, in the case of a roof system, yeah, there's a really good reason. We want the rain and the snow to drain off, so yeah, we use them. In bridges, you only tend to see trusses used nowadays when the bridge gets really long, okay? And we're talking really long. I could go on and on about how trusses are considered fracture critical. That is a very bridge engineering concept, which I might talk about later. So we avoid using trusses a lot these days for that very reason, but I will open up a big ball of wax if I get into that, and I do want to get into our topic in here. So like I said, when we analyze a truss, we are analyzing a truss for specific assumptions, okay? So let's talk about these assumptions, okay? Essentially, there are three of them. When we analyze trusses, we make the following three assumptions. The first is that all of the members are connected by frictionless joints, okay? And basically what that means is that when you apply force to a given truss, that there's no unintended forces or moments that arise from friction, from members rubbing together or what have you, that the forces that you're accounting for are basically the only ones that you need to consider. The second assumption that we consider is that all of the loads and support reactions are applied only at the joints, okay? So if I go back a couple of slides, if I look at, let's say, this truss, if I were analyzing the truss, I would only analyze the truss if a load is applied at this joint, or this joint. I would never consider a situation where a load is applied directly on the member. If I had something like that, what I would do is I would distribute that load to the adjacent joints and analyze the truss that way. But also when we design trusses, we sort of design them and configure them so that that doesn't happen very often. So we only apply loads or support reactions directly at the joints. But another big one is that at each joint, the centroidal axes of each members coincide. So what that means is if I look at, let's say, this image of a truss joint out in the field, we can see I've got 5 members, and this is all riveted. We don't really use rivets anymore these days. But you can see if I sort of imagine like the central line, where the centroid is, of each member, they all meet at a common point, okay? That's not by accident. That's done on purpose, okay? The idea behind that is that we reduce shear and moment, okay? You all had statics, right? Do you remember one of the very first topics you do in statics is statics of particles? It's like the first thing that you do in the class is you learn about sum of forces equals 0. You don't actually talk about sum of moments until a little bit later in the class, okay? The reason why is because in statics, we deal with concurrent force systems and we deal with non-concurrent force systems. A non-concurrent force system is when the forces don't all meet at a common point. And if that's the case, you have to balance both forces and moments. But for each truss joint, by making these assumptions, and a lot of them aren't really, some of them aren't really assumptions. We're actually like fabricating the members so that all the centroids coincide. What we're dealing with is a concurrent force system. What these assumptions do is basically say, all right, if we break out the secret weapon of structural engineering and we start cutting sections with samurai swords or lightsabers, if we happen to be sci-fi fans, what happens is when we cut a section through an arbitrary structure, we get 3 unknowns. But for trusses, we only get 1. And the reason that we only get 1 is because of all these assumptions that we make. We assume all the centroids of each member coincide. We assume we only apply loads at the joint. We assume no other forces from friction or anything like that. So when you cut a section through a truss member, there's only one force, an axial force, a force along the axis of the member. That's why whenever you analyze a truss, you're basically trying to figure out whether or not a member is experiencing tension or compression. That part you probably remember, right? Tension and compression in truss members. If not, don't worry, we're going to have some practice on that. Okay, everybody with me so far? Okay, so there are 2 primary methods of analyzing a truss. And maybe I should be a little bit more specific about my terminology when I use the terms analyzing a truss. When I say analyze a truss, what I mean is this. I mean determine the internal forces in all of the members inside the truss. So what is member AF carrying? What is member IJ carrying? What is member EK carrying? Or what have you? What are the internal forces inside those members? And there are 2 primary means at our disposal. The first is the method of joints, and the second is the method of sections. Is this all ringing a bell? Probably remember this, right? Now, as structural engineers, if you ask me which method is more important for, like, I don't know, your career, I would honestly say the method of joints, because more often than not, when we're in the process of analyzing or designing a truss, we're ultimately going to need the forces in every member, not the forces in some of the members. Granted, I will give you, I will grant you that the method of sections is a lot better for quickly checking the force in one member or quickly checking a result for a given analysis. But the method of joints is a lot more methodical. It's a lot more thorough. It is tedious, but the beauty of the method of joints is, for one, you have less equations of equilibrium that you have to deal with, but 2, it'll give you the solution for the entire system. Okay? So the way that the method of joints works is we analyze the equilibrium of each joint. Like, the idea is that if the whole structure is in equilibrium, then each joint has to be in equilibrium as well. And so we just assess the equilibrium in each joint one by one until we get through the whole structure. Method of sections is for spot checking, but we'll get into that a little later. Now, the method of joints looks at each joint one at a time, but what we are dealing with is a particle statics problem. We are dealing with a situation where all the forces all meet at a common point, okay? We have no friction, we have the centroids aligning, we have the loads applied directly at the joints. So we investigate the equilibrium of each joint, but because all the forces meet at a common point, we only have 2 equations of equilibrium. There is no moment at a joint. I mean, how do you generate a moment? Like, if I have a force and I have a point, how do I generate a moment about that point? I have to have the force separated by some moment arm in order to cause it to rotate. But if the force is going directly through the point, there is no moment, right? All the forces in a joint all go through a single point, so there is no moment. So we only have 2 equations of equilibrium. Now, that does mean there's a limit. Whenever we apply the method of joints, we can only use the method of joints on a joint that has at most 2 unknowns, okay? And that'll become pretty apparent as we start solving problems, okay? Speaking of, let's go ahead and do one, okay? Now, I want to go through a couple things with this example before we start knocking it out. Let's take a look at what's going on here. So I have a truss here. We're going to determine the internal forces in this truss utilizing the method of joints. Okay, there's a lot going on here, so let's just sort of take stock of what's here. So I have a truss. I've got 1, 2, 3, 4, 5 joints. Okay. I've got them lettered. Okay, joint A, joint B, joint C, joint D, joint E. I'm doing that. I'm doing that so that we, as a class, will be able to refer to the same joints in the same notation. Sometimes what you'll do is you'll see, in practice, you might see this joint called L0, L1, L2, or something like that, and this might be U1 or U2 for like lower and upper. I might talk about that notation a little more later. I don't really want to confuse things. But for now, we'll just call them A, B, C, D, and E. So there's that. What else have I given you? I gave you the support reactions. Okay? I'm going to tell you why I gave you the support reactions. We know how to do this, right? Do we really need to waste time in class computing support reactions for this truss if we've been computing support reactions for the past week and a half? I don't think we need to go through that. So there's a vertical reaction here and a vertical reaction here and a horizontal one, right? There's 15 kips to the right, so there have to be 15 kips to the left. So all the support reactions have been computed. Some problems, you're going to be given the support reactions. Some problems, you're going to have to compute them. On your homework, you're going to have to compute them. But that's just to sort of shake the rust off from truss analysis and whatnot. Another thing is these diagonals, okay? Every diagonal goes over 6 feet and up 8, over 6, up 8, over 6, up 8, over 6, up 8. So every diagonal is at a 3 to 4 slope ratio. That's going to make our analysis a little bit easier to bookkeep. Next time on Friday, we're going to do a truss analysis where the members are not at the same slope ratio. They're at different slope ratios. So it's not going to be any more difficult, just going to be a little bit more bookkeeping to handle as we go through our calculations. All right. Okay. All right. Is everybody with me on this so far? Anybody have any questions? Okay. All right. So here's what we're going to do. Okay. We are going to start analyzing this truss. Okay. Now, I am going to walk you through the first joint. Okay. And I'm going to start alphabetically with joint A. Okay. I'm going to walk you through this one. And then I'm going to start asking you for help on how to do the remaining ones. So, it's sort of like we're going to start pedaling with the training wheels on, and then we're going to start unbolting the training wheels one at a time. So let's see what happens. Okay. Okay. So let's do that. Okay. I'm going to start off with joint A. Okay. So I try and be pretty systematic with my truss analysis. I would argue the most common mistake that I see students making when they perform truss analysis has nothing to do with the statics or the physics or the math of the situation. It usually has to do with bookkeeping. It has to do with forgetting something, forgetting an error, forgetting a force. So try and be pretty methodical with it. Okay, so this is sort of how I do it. The first thing that I do is I draw the members framing through joint A. Okay, so the members that go through joint A are this diagonal and this diagonal. In other words, this is joint A, and there's two members going through joint A. This one and this one. Okay? Everybody with me on that? Okay. The next thing that I will do is I will write down any slope ratios for any diagonal members that I know. That's a 3 to 4. Everybody okay with that? Okay. Now, the next thing that I will do is I will write down any forces going through that joint that I now know before I do any calculations. How many forces do I know that are going through that joint? 2. I have a vertical force going through that at 12.5 kips and a horizontal at 17.5. With you so far?
The horizontal 15.
Oh, yeah, it is 15. You're right. You're right, 15. Okay. All right, now let's put ourselves a little thought bubble over here. I want to make a point about something. Let's talk about this diagonal member real quick. Let's talk about this diagonal member, okay? This diagonal member is going like this. Now, it's a truss member, so let's see if you all remember this. If I cut a section through a truss member, how many unknown forces are inside a truss member? One, right? An axial force, right? Okay, now I propose inside that truss member, that force is either going to go one of two ways. It's either going to go like that, or it's going to go like that, right? Okay. Do y'all remember from statics, tip to tail vector addition, right? And do you all also remember from statics how we can break a vector up into its x and y components? Okay, if I were to draw a coordinate system like right here, which quadrant would this vector be in? 1, 2, 3, or 4? This one? This is in quadrant 1, right? Remember? Positive x, positive y. So if I were to split this vector up into x and y, it would be like that and like that, right? Okay? This vector over here on the right, if I were to split this up into x and y, it would be down and to the left. With me so far? In other words, could I do this? Could I do this? Does this make sense? No, this doesn't make sense, right? This is wrong, right? So the idea is that if here's my joint, okay, if here's my joint, my x and y components either need to both be away from the joint or they both need to be pointing towards the joint. Does everybody see that? Everybody okay with that? Okay, they either have to both face the joint, so this one's pointing towards the joint, this is pointing towards the joint, or they both have to be facing away. That's an easy thing to get backwards, okay? Or get one right and one wrong. Okay. So far so good? Okay. All right. The next thing I like to, okay, so with that being said, let's just sort of go through my truss or my joint analysis. So I've got joint A here, okay? I have a horizontal member. This horizontal member has an unknown, okay? Now I'm going to call the unknown AB, okay? Now this is a diagonal member. This diagonal also has a single unknown, which is going to be AD. But because it's a diagonal, what I'm going to do is I'm going to split it up into X and Y. Okay? And so we'll call this ADX, call this ADY. Is everybody following what I'm doing so far? Anybody have any questions? Anybody confused? Everybody good to go? Okay. All right, so looking at it this way, how many unknowns in the horizontal direction do I have? 2. How many unknowns do I have in the vertical direction? 1. Okay, now to be clear, these two are related. They're dependent upon one another. But if we're just looking independently, I have 2 in the X, 1 in the Y. Now remember, when I'm solving a truss or a method of joints problem, I only have 2 equations of equilibrium. Like each joint only has 2 equations of equilibrium, X and Y, forces in the X direction, forces in the Y direction. There is no sum of moments. So I guess my question to the class is, if I were to solve this joint, which one would you do first? Sum of forces in the X direction, sum of forces in the Y direction. Y. Okay, correct, because I have one unknown. So help me out. If this is 12.5 kips going up, what is that? 12.5 kips going up. Exactly. So what I'm going to do is I'm going to draw this arrow going down, and I'm going to say that. That's got to be the case. So far, so good? Okay. Now, I propose that if I know this, I know that. How? Okay? Here's how. If I know this and I know that, how would I calculate the hypotenuse? Keyword hypotenuse. Pythagorean theorem, right? So this value has to be the magic value such that this squared plus this squared times the square root is aligned this way, right? So how do I do that? With the slope ratio. So I propose the following. I propose, I propose that ADX is to 3 as ADY is to 4. And I'm just saying that the horizontal component is to this component as the vertical component is to this. Because when I apply Pythagorean theorem, it's got to go this way. It's got to go parallel to the member because it's got to be axial, right? With me so far? Now, by the way, before we do any math, can somebody tell me which direction ADX is facing? Is ADX pointing to the left or to the right? Left. To the left, because it's got to be pointed towards the member. So therefore, ADX is 3/4 ADY. That I think is like a alert system thing. Hold on. Sorry. I'll deal with that later.
It's a test.
Yeah. Did everybody get one? Yeah. So, somebody help me out. Casio FX 115 ES Plus or similar scientific calculator. What is 3/4 of that?
9.375.
9.375. Do I have a second? Okay. Okay. Is everybody with me so far on this? So, what's left to solve for? Am I done? What am I missing? Which way is AB facing, do you think? To the right. Why is that? Because this and this are to the left. So AB's got to go to the right to maintain equilibrium. Does everybody see that? Okay, so that means that if I, so therefore, if I sum forces in the x direction, what is AB? $24.375. Do I have a second? Okay. So far, so good? Okay, so let's do a summary real quick. So we have member AB is 24.375 kips. Now here's the thing. It's 24.375 kips to the right, but the right or left or the arrow direction is only relevant for this joint analysis. What I am mainly interested in is whether this member is experiencing tension or compression. Okay? Now, the easiest way to do that is to just look at the joint in question. Is AB going towards the joint or away from the joint? Away. So if I'm here and you're pulling away from me, are you applying a tensile force or compressive force? Tension, right? Here's a rope, you grab the rope, pull it away, we're applying a tensile force to the rope. So AB is experiencing 24.375 kips in tension. Now, what about member AD? Is member AD experiencing tension or compression? Compression. Because both forces are pointing towards the joint. What is member AD, by the way? How do we do that? There you go. Okay. How are we doing? So far, so good? All right, any questions on this? Everybody good for our first joint analysis? Okay. All right. So let me ask you a question. Let's go back to the original truss image. Okay. So here's what I'm gonna do. I'm gonna break out my highlighter. Okay. And here's what I'm gonna do. I'm gonna highlight this member and this member. Now, why am I highlighting those two members? Those are the ones I just solved, right? Okay. Now, let's go back a little bit. We solved joint A first. And when we solved joint A, how many members were going through joint A? How many, pieces of steel, as it were going through joint A? Two. And we had two equations of equilibrium, right? With me so far? So we did joint A. Let's do joint B. Is that a problem? It is a problem. Why is it a problem? Because all right. So I think you said 4 unknowns. It's not, or did somebody say 4? Okay. Well, it's not 4, it's 3. Right now it's 3. Right now there are 1, 2, 3 unknowns going through joint B. Okay? Right now there are 3 unknowns going through joint B. We can't solve joint B right now. We don't have enough information to attack joint B right now. Okay? And so we're going to talk about this later, but whenever you start doing a truss analysis, one of the things that's valuable is to actually plan a strategy before you start just doing joint analyses. In other words, like if I do joint A first, that's going to give me these forces. So then I'll do this joint and it'll give me this one. So then I'll do this joint and it'll give me this one. So I can figure out how I'm going to solve the truss from beginning to end. Speaking of, could I go ahead and do joint E right now? Yeah. Joint E? No, because it also has 1, 2, 3 unknowns. What about joint C? Could I do joint C? Yeah. I could do joint C. Nothing's stopping me from joint C. What about joint D? Yeah. I could do joint D too. I could do either joint C right now or joint D right now. Now, I am going to choose to do joint D from a purely educational reason, because I want to make sure that when we're doing joint D that we're able to track our data appropriately. Okay? And you'll understand what that means here in a second. Let's do joint D. Okay. All right. So whenever you do a joint, like I said, I'm going to track this the same. I'm going to go through and draw my images and write down my calculations the same way that I did this last time. Okay. So how did I do it before? Okay, so the first thing I did is I said, let's draw all of the members that are going through joint D. Okay, so So that's all the members that are going through joint D. Okay. Next thing that we're going to do is if there's any diagonal members, we'll do our slope ratios. So four and three. Next thing that we're going to do is our known forces. First off, does joint D have any loads applied to it? What load? Going down. Okay. Now, Now we chose joint D because this member and this member were unknown, but that begets the idea that this one is known. We know the X and Y component of this diagonal over here. We know what's going on this one. Okay, help me out. What is the horizontal component on this?
9.375.
What is the vertical component?
12.5.
Okay. Now the big question are the directions. Which way is the 12.5 going, up or down? Up. Okay. What about the 9.375? Okay. That's backwards than what we had before, isn't it? Because up here, we had 9.375 going to the left. Now you have it going to the right. Up here, we had 12.5 going down. Now you have 12.5 going up. It's because we're on the other side of the member, right? If I have this marker, and I want to apply a compressive force to this marker with my hands, and if I want to apply compression, my hands are applying forces in opposite directions. This hand's pushing that way, this hand's pushing that way, right? But we're both doing the same thing to the marker, right? Both hands are doing the same thing. The same idea here. So on the other joint, on the other side, the arrows split the direction. So far, so good? Okay. Now for my unknowns. Same as before. Diagonal's going to have 2. This is going to have 1. Let's name these. Let's call this DE. And BDX and BDY. So tell me what I should do first. You tell me now.
Some forces in the y direction.
Sum forces in the y direction. So if I sum forces in the y direction, what does that tell me? What do I get? BDY. What is BDY going to be?
225.
Going down, because I got 12.5 up, 10 down, so I got to have another 2.5 going down. And by the way, if you need to draw a table to actually sum this out, go for it. No problem. We are going to have some joints where that might actually not be a bad idea. So far, so good? If I have one component, how do I get the other component? How did we do it the last time? The slope ratio. So, BDX is going to equal some fraction times BDY. I propose that that fraction is either 3 over 4 or 4 over 3. Which is it?
3 over
3 over 4. How do you figure that out? The horizontal is smaller, right? We're solving for the horizontal. So just put the horizontal and the vertical. So. Oh, man, sorry. Touchscreen. So what is 3/4 of that? What is 3/4 of 2.5? And which way? So tell me what to do now.
Some forces in this direction.
And what does sigma f sub x equals 0 give us? dE equals what? So what do we have going horizontally? We have 9.375 to the right, but we also have this to the right, which is this. So we have that and that going to the right, which means we need something going to the left. And what is that going to the left?
11.25.
11.25. Does everybody see that? So if you want, you could say, you know, I mean, you could do it like that if you want. You could say, all right, I've got this and this going to the right, and I have that going to the left. If you need to do it that way, that's totally fine. Okay? And yes, that is going to the left. So let's put that like that. So, oop. How do we solve for BD? Pythagorean theorem, right? And what do we get when we apply the Pythagorean theorem to member BD? Which force is that? Is that tension or compression? And how about DE? And it's 11.25 kips in compression. So far, so good? Okay. How are we doing on this? Okay. So, which joint did we just solve? D? So that gave us that and that, right? Any problem with doing B now? Let's do it. Let's do joint B. Now, I'll say this. Joint C is probably easier because there's less bookkeeping, but part of the challenge with truss analysis is that you are going to have to do bookkeeping whether you like it or not. So I would rather nosedive into that. Let's do one that's going to have a lot of arrows in a lot of different directions to make sure that we're comfortable with it. Let's do joint B. There's 4 members going through it. So what? Let's do it. But before I move on, does anybody need to write this down? Everybody good? Good? Everybody else good? All right. So let's do joint B. All right. Same idea. Okay. Okay. Truss members. Next off. Three and four. Okay. All right. Any known for? Is there any load applied at joint? External load applied at joint B? What is it? Okay. 20 kips. Do we know the force in this member? This horizontal member right here? Okay, let's handle it this way. Okay, so the first thing I want to ask you is what's the magnitude? How much force is that? Now, was this member in tension or compression? So if it's in tension, which way do I draw the arrow? To the left. All right. What about vertical and horizontal right here? Do I know those? What's the vertical? What about the horizontal? Okay. Do I know the, was it tension or compression? This one was, that one was compression?
Oh, wait, that, okay.
Yeah, this is tension, right? So if this is tension, vertical, up or down? What about horizontal? So I've got that. This is BC. This is BE. All right. So what do? You tell me. Some forces in the Y. And if I sum forces in the Y, what does that tell me? And what is BEY? 17.5 in which direction? So this is up, which means that is to the right. And how do I determine BEX? I use the slope ratio, right? Slope ratio BEX. Every member in this truss has the same slope ratio, so we do it the same way we've been doing it before. That won't be the case on Friday. And what is 3/4 of that? Three-quarters of BEY.
13.125.
Do I have a second?
Yeah.
All right, 13.125. This one's starting to get a little messy from the bookkeeping perspective, isn't it? So why don't we do this? When we sum forces in the X direction, let's do this. So what do we got? 24.375, 1.875, both acting to the left. 24.375. I can do better now. What about to the right? Well, I've got BEX. All right. So you tell me, does BEX, does BC, do you think BC is acting to the left or to the right?
Left.
The left?
Oh, right.
Yeah, because look, there's a lot going this way. We need more going this way, and that's supposed to be 24. I don't know what happened there. So we need to do that. And I know we're running short on time, so what do we got? We got 26.25 is BC plus 13.125. Say it again. Yes. So that means BC is going to be also 13.125. Going to the right. So far, so good? I know we're running short on time. Here's what I'm going to do because we're running short. Okay. I'm going to stop the in-class work here. Okay. But what I'm going to do is I'm going to finish this truss on a separate recording. It'll only take me like 5 minutes. I'm going to post that on the YouTube playlist just to do the whole thing and finish it. Okay. What's that?
Can we talk about it next time?
Oh, yeah. We'll talk about it.
Okay. So like you'll go ahead and do it and just like talk us through it.
Yeah, so what I'm going to do is finish this example, put it on the YouTube recording. There'll be a homework, but the homework is the truss is a little bit smaller. So,
Okay, good.
all right.
That one was
I know. Trusses do tend to be long. All right.
but that's pretty much what you do for all of you, just like go around to each one.
Yeah, you just keep going. All right, let me stop this.